In this video, I'll go over how to apply the shooting method to nonlinear differential equations. After studying this video, you should be able to formulate the shooting method as a roots problem when applying the strategy to a nonlinear ordinary differential equation, and implement the shooting method for a nonlinear boundary value problem. Recall that the shooting method algorithm is a combination of tools that we already have. The first step is to convert the boundary value problem into an equivalent initial value problem. Then we're going to guess any undefined values for the initial conditions. Often that's going to be guessing dy dx at x equals 0. We'll take that guess, use an initial value problem solver to integrate the differential equation, and modify our guess until we want our end of the integration to hit the target. And that's always going to be our second boundary condition, in this case YL. So we'll change those guesses until we find the initial guess that hits the target. In the previous video, we saw that for a linear differential equation, we only need 2 shots, and then we can use linear interpolation to find the initial guess that hits the target. For a nonlinear differential equation, we're going to have to set this up as a roots problem because linear interpolation does not get us to the correct guess. So let's look at how we do that. So the basic idea here is to treat the endpoint of the ODE integration as a function. Here's our ODE function dy dx, and we'll call ODE 45 or some other initial value problem solver to integrate that function with an initial guess for our second boundary condition, and we'll just call that z. And then we'll define this function f of z as where did we end up. So this is our end point of the integration. So the idea of this function is, coming back to our shooting method algorithm, is z is our guess at the slope, if the slope is our unknown initial condition. It's the guess at the slope dy dx at x equals 0. If we do that guess, then we put that into our function, and the result of the function would be our end value. So that would be our f of z. So now that we've defined that function, f of z being the end value of our integration given an initial guess z, we know that the accurate shot is going to occur, well, f of z is equal to YL. And we can use that to formulate a roots problem. So the residual in the roots problem, we call that concept of a residual. So the residual of the roots problem is going to just be f of z minus YL. And we want to find the value of z. Find the value of z. Again, that's our initial condition guess, such that f of z equals YL, or f of z minus YL is equal to 0, or the residual of the roots problem, f of z minus YL, is equal to 0. So again, our basic roots problem is saying f of z is equal to YL. Then we'll use the root finding method to solve the roots problem. So we can use F0, Matlab's built-in function for roots problems. Finally, we'll use that result of z for the initial condition guess to finally integrate our ODE to the target boundary condition. So let's look at how this works with an example. So here's a nonlinear boundary value problem to solve for the temperature distribution in a heated rod. So the temperature distribution is described by the following differential equation. We have the second derivative of temperature with respect to x plus h prime times t infinity minus t plus sigma prime times t infinity to the fourth minus t to the fourth is equal to 0. Let me define some of these parameters. So T infinity is just the ambient temperature. So in this case, we're saying we have a rod out in an ambient temperature of 200 Kelvin, and the rod's heated because on the left-hand side, we'll call this T0. That's equal to 300 Kelvin. That's one boundary condition. And on the right-hand side of the rod, we'll call this TL. That's equal to 400 Kelvin, or at x equals 10. The two coefficients, h prime and sigma prime, are bulk heat transfer coefficients, combining the effects of conduction and convection in h prime and conduction and radiation in sigma prime. So what we're going to do is use this differential equation to solve for the temperature distribution T of x. So here is the Matlab code to solve this problem using the shooting method. And we actually need 3 M files to make this work. So our first M file here, what we're doing is using F0 to find the initial condition guess that hits the target. So we'll use F0 to call a function barres, which is the residual, the function that defines the residual for F0, and this is just our initial guess. So let's first look at barres. So barres is down as actually our third function on this slide, down here. Here's barres. And what barres does is takes our initial condition guess. Remember, we're using F0 to solve that roots problem for the initial condition guess. We take that initial condition guess. We're going to use it here as our second initial condition to call ODE 45. And we call ODE 45, take the last value and subtract TL, and this gives our residual for the roots problem. Then again, F0 is now using that function barres to find the value of x such that we want that r to go to 0. Bar temp, the other function involved here, that's our dy dx, and we see bar temp again here. And now in this, we've often been using anonymous functions to define our ODE functions, but in this case it really makes sense to use an external file. So I've done that in our third M file right here, and the reason it makes sense to use an external file is because we're calling it once from our main file, the same file that we're calling F0 from, and then we're calling it a second time from the function file that defines barres. So in bar temp, we see our constants are defined here, and then just as we've been doing, we define dt dx as a system of two first-order differential equations for the initial value problem solver that we're using, ODE 45 in this case. So let's go through this one more time. So what Matlab does is, the first thing we're doing is we're using F0 to use this residual function where we take the final value from the integration, subtract the second boundary condition, and we want that to be 0. So that's our roots problem. F0 is going to find the value of IC guess which is what the value of x is in our general f of x formulation for f0. That translates to IC guess. F0 is going to find the value of IC guess. Then we're going to use that value of IC guess that we have here as our second initial condition to send to ODE 45 for our final integration. So we might have, depending on how many iterations it takes for f0, we have, say it takes 10 iterations for f0. To solve this one problem, we're going to call ODE 45 11 times. One time for each of the 10 iterations of f0, plus a final time with our successful on-target initial condition. So let's look at the result. So I've shown the figure again here so you can kind of visualize what's happening with the temperature. We have heat transfer due to radiation, conduction, and convection considered. And as we expect, our boundary conditions, we have 300 at the left-hand side and 400 at the right-hand side at x equals 10. And the temperature decreases as we go along the length of the bar and then increases back up to 400, hitting a minimum value of about 240. So I'd encourage you to download these M files, step through them to really understand what is going on as f0 is calling our bar res function and then going to ODE 45 to get the value it needs for the end of the integration to formulate the roots problem, and finally iterating in f0 to find our on-target initial condition guess and use that as the second initial condition for the final integration with ODE 45. And that concludes this video.